Gravity is the most pervasive force in the universe. It is at work on massive and minute scales, on the routine and the extreme. A surfer needs it to hang 10. A skier uses it to race downhill. A snowboarder must have it to get big air. It acts on everything with mass, including us, 24/7, even when sleeping or standing. At a theme park, gravity is the galactic gas that makes roller coasters roar and people scream. All objects with mass or energy, particles, people, planets, stars, and galaxies produce gravity. Omnipotent and omnipresent, gravity attracts, governs, warps, shapes, makes, and takes all matter and mass in the universe. It is gravity that holds our solar system together. It is the cosmic glue that binds all matter in the universe together. Gravity made our world. When it comes to gravity's pulling power, mass and distance matter. In other words, the bigger it is, the harder it pulls on other objects. But that's not all. This means if you double the distance between two objects, the attraction or pull is only a quarter of its original strength. The pulling power of gravity lets it direct the motion and movement of all matter, however massive, in the universe. But it is the practical potential of harnessing this relentless force that has obsessed scientists for centuries. It would literally fall to Galileo Galilei, the 17th century truth seeker, to first recognize that gravity even existed. But why doesn't the moon fall to Earth?
The moon also has some sideways motion. So for every little bit that it falls down, it also moves off in this direction, and the sum of all those motions is an orbit around the Earth.
Newton also realized that the Earth is in a giant free fall around the Sun. With gravity forging the path, our planet rounds the Sun like an endless cosmic roller coaster ride. Newton cracked the gravity code, and physicists are still using his ideas to solve all sorts of problems. Some of them stranger than others, like what would happen if a person tried to travel through a tunnel from one side of the planet to the other? In this wild scheme, you'd have to drive a straight-line tunnel right through the Earth and use gravity alone to propel a traveler down this so-called gravity express.
So suppose you've got one of these tunnels and you jump in. Initially, the Earth is pulling down. You're going toward the center of the Earth, and so you're accelerating toward it. But as you pass through the center of the Earth and start going out toward the opposite side, the gravity of the Earth is trying to pull you back, so it's decelerating you.
So gravity is actually have a braking effect. There's no fear of shooting out the hole on the other side of the Earth at some tremendous velocity and shooting yourself back into space. But in fact, you reach the surface of the Earth exactly, you were close to a perfect rest. In 42 minutes, you'll be there.
Whichever two cities you connect with a straight-line tunnel, it takes gravity exactly 42 minutes to get you there.
The journey from Los Angeles to Paris, 42 minutes. Suppose you wanted to go from Los Angeles to Tokyo, 42 minutes. It doesn't matter which path you take through the Earth, the journey is always 42 minutes long.
It takes Newton's math to figure out why this works.
If we connect Los Angeles to New York, taking a tunnel, obviously the tunnel would not go straight down, but it has to go down at an angle.
The angle slows the speed of descent.
But the distance is also less, and if you work out the equations, Lo and behold, the two effects cancel, and you still get there in 42 minutes.
Newton figured out what gravity does, but it took the brilliance of physicist Albert Einstein to work out why it was doing it. Einstein realized that gravity is really caused by huge objects like stars and planets literally bending space itself. Like a massive rubber sheet, space is curved when massive objects sit in it. In fact, Einstein proposed that the path planets take around their stars, their orbits, are all a direct result of this curvature of space. This revolutionary discovery came when Einstein, in the early 1910s, realized that orbits of stars and planets in the observable cosmos behave just as Newton's math predicted, except one, Mercury. Its orbit essentially wobbles.
Einstein described gravity as a curvature in space and time, and the orbit of Mercury works perfectly when you take that into account. Mercury isn't moving in flat space, but curved space around the sun. Then the orbit's perfect.
This curvature of space is at play in our own solar system. Einstein not only determined that mass warps space, it warps time too. Einstein's realization that space is curved and that time and space are in fact intertwined is now the very definition of gravity. Gravity is our friend and our foe. It is the fearsome force that propels a skier and the snowboarder down the mountain and shoots them into the air. With enough momentum, an airborne snowboarder can feel, for fleeting moments, as if they are free of Earth's gravitational pull. In the end, gravity wins, and the high-flying, free-falling boarder, just like the ball fired from the cannon, is eventually yanked back down to Earth. To get to Mars and beyond, mankind will have to harness gravity's energy. Just like we always do when we're seeking thrills to the extreme. Gravity gives us two types of energy: potential and kinetic. Potential is just that. It's energy that's being stored, while kinetic is the result of all that pent-up potential energy. This fantastic phenomenon works on a roller coaster. NASA also uses this energy exchange principle to add some speed to their missions. As a spacecraft nears the orbit of a planet, it too gathers kinetic energy at the expense of potential energy. Then, as it rounds the planet on its cosmic coaster ride, the craft gets a slingshot effect that punches it onward with more kinetic energy. Knowing how to use the power of gravity will enable humanity to travel further and faster across the universe. Far away from Earth's gravitational pull, in a spaceship on the long journey to Mars, for example, future astronauts will have to learn to live, work, and play in an environment free of Earth's sizable gravity. One where they effectively feel weightless and all objects move equally and freely. At the dawn of the 21st century, overcoming the bonds of gravity and escaping Earth's sizable tug have been realized. The next step is to design and build the technology that will allow humans to travel, work, and live on exotic alien planets. Thanks to state-of-the-art technology, humanity is on the brink of a new era in space exploration. Since the advent of the space age, scientists have been concerned with minimizing the life-threatening risks and damaging effects of being weightless at 0 G. A mission to Mars would require astronauts to be away from Earth's gravity for at least 2, maybe 3 years. The human frame is simply not designed for the absence of terrestrial 1G gravity. Experience has shown that being weightless for long periods leads to bone loss, muscle deterioration, and life-threatening blood clots. Aeronautical engineers at NASA and MIT are testing a personal centrifuge system that may mitigate the very real dangers. Just like a theme park ride, spinning a subject artificially creates G-forces. To prevent motion sickness in the MIT ride, astronauts are conditioned to keep their heads still. By spinning a person at 30 revolutions a minute, the centrifuge imparts 1G, the same force felt pulling down a person standing on Earth. Scientists hope that one day a trip to Mars will be a reality. On board, they believe there should be a personal centrifuge. To get their earthly gravity fill-up, 21st century astronauts could then just spend 1 hour a day on the machine. A person who weighs 100 pounds on Earth would feel as if they weigh 38 pounds on Mars. Although a Martian skier would fly down Olympus Mons at a third of the speed they would on Earth, the lower gravity also means they could get at least 3 times the big air. The big kahuna in our solar system is Jupiter. On that planet, a 100-pound person would weigh a whopping 254 pounds. Even if Jupiter had a solid surface, a skier there would have to fight for big air. What we already know about gravity, how it works and how it can be used for practical purposes, it could, in theory, even save the planet from its ultimate cataclysmic fate. Here's how gravity can come to our rescue. Gradually, in about 5 billion years, our sun will brilliantly flare, turn into a red giant, gloriously burn up, and die. As this comes to pass, our inner solar system is engulfed, and Earth's gravity and atmosphere will be radically altered. At that point, life on the blue planet will end.
This environment that we have here now would look very similar to the environment that is holding sway on Venus right now, crushing carbon dioxide atmosphere at temperatures hot enough to melt lead.
But rest assured, if the worst hypothetical happens, gravitational science could save Mother Earth.
The one thing that we could do over the very long term is to somehow move the Earth's orbit out to a larger distance from the sun where the temperature isn't so high. And a way that you can do that, if you have enough time, if you have billions of years available to you, is to use a comet or an asteroid.
This mega move would require astronauts and engineers aboard a spacecraft to maneuver the comet or asteroid just in front of the Earth.
In order to be most effective, the comet has to fly very close to the Earth, within an orbital radius or so of the Earth.
Then, on the cosmic roller coaster, potential and kinetic energy are roused, and gravity does the rest.
If that happens, then the comet pulls the Earth forward, the Earth pulls the comet backward, and the net result is that the Earth is given a boost. It's given a boost to a slightly higher orbital radius, slightly larger distance from the sun. And if you make one of these adjustments, one of these passages every 10,000 years or so, then the Earth over a period of 1 billion years can move at a fast enough pace outward to keep track with the steadily brightening sun.
If, however, the experts get the math wrong and the big gamble doesn't work, all bets are off.
If you screw that up, then you can have a collision between the comet and the Earth. So a 100-kilometer object crashing into the Earth is absolutely an extraordinary disaster. It's the kind of thing that causes huge extinctions of gigantic numbers of species.
Of course, this is only an extreme hypothetical scenario, but what is known for sure is that our continued existence today here on Earth is contingent on the presence of gravity. It allows for the perfect conditions for life and the pursuit of happiness. Tidal torrents of gravity-boosted particles roll across the cosmos. According to Einstein, these gravitational waves wash through the universe. But what are they?
Any change in the gravity sends a ripple through that fabric of space, then moves at the speed of light. That would be a gravity wave.
And why do they happen?
If you have two objects, two compact stars, each of which curves space around them, and they're orbiting one another, then the result is that these two curved regions create a wave, a ripple in the structure, in the shape of space that moves outwards, carrying energy with it. That's called a gravitational wave.
But for Earth-bound scientists to detect any faint G-wave signals, the disturbance needs to be propagated by a massive cosmic object. Black holes and spinning neutron stars can do it. The tool to catch the light-like signal from a wave is the LIGO, the Laser Interferometer Gravitational Wave Observatory. There are two identical ground-based LIGO labs. One is in Hanford, Washington, and the other is more than 2,000 miles away near Baton Rouge, Louisiana. If a wave comes by, each lab's results will be vital to confirm the event. Here's how it works. Super polished glass mirrors are at the fulcrum of the interferometer, which is a tool that basically compares two light wave measurements and identifies the differences between them. Precision laser light is fired back and forth and split between two calibrated mirrors. In normal circumstances, as the light bounces up and down the 2.5-mile-long L-shaped vacuum tubes, the two laser beams are basically in sync. This means the beams effectively cancel each other out and no light escapes the tunnel. But when a gravity wave rolls through, space is ever so slightly stretched or squashed. As a result, the laser beams are thrown out of phase, and only then a small amount of light is emitted. A tiny signal, less than the diameter of a human hair, 1/1000th the size of a proton, will register. Converted into a sound and a light signal, it will be seen and heard. The scientist's greatest hope is to catch the most massive event that ever occurred in the universe, the Big Bang. The force of gravity has domain over our universe. It created and can destroy the cosmos, the stars, the planets, and the people. It controls our lives, our play, and our endeavors. Our collective future depends on the grace and greatness of the mighty ruler of the cosmos, gravity.